Okay, ladies and gentlemen, now we notice that how the voltage generated by varying angle with time. Now we look at here, if we view from the top, from the side of the coin, where the cross-sectional area of the area of the coin is 0.5 meters square. Magnetic flux is equal to 1.5 Tesla, and the time is 1.5 seconds. So we start the motion. So in 1.5 seconds, so it turns how much? It's turned 90 degrees in 1.5 seconds. Okay. So how about from the top view? This initially is like that, once turning 90 degrees. So turning with 90 degrees. So ladies and gentlemen, how is the change? EMF is equal to negative N, the change of the magnetic flux over dt. Initially it's BA cos 90, right? Because parallel. After that, final will be equal to, BA cos 0. Initially, BA cos 0, final BA cos 90. So divide by the time, we get that 1.5 seconds. And finally, we get the EMF is equal to negative 2.5 watt. Negative show that the direction. Then if we just want, you also can write how much of the EMF produced, because we just want the magnitude. The magnitude is 2.5 watt. Okay, so negative 5 times with negative 0.5, then we get that 2.5 watt. So that means that the EMF produced in the coin, when it's turned for turning, rotate for 90 degree distance. The EMF generated or EMF induced is equal to 2.5 watt. Now, let's observe the next slide. Okay, first we can make a conclusion. Faraday's law states that the induced EMF in a coin or a circuit is directly proportional to the rate of change of magnetic flux through the coin or the circuit, where the EMF is equal to negative the change of the magnetic flux over the change of the time, where delta phi b is the magnetic flux treating the circuit or coin. dt will be the time taken. With n turns, the expression become EMF equal to negative n d phi b, that means change of the magnetic flux over the change of time. And induced or generated EMF can be produced in a number of ways. So we can use the formula either EMF equal to NA dB over dt, or we can use EMF equal to negative N B dA over dt. If you use this one where A is varies with T. If we use dB dt, that means B varies with T. We also can use EMF equal to negative N, change of the magnetic flux over the time. So that means use BA cos delta 2 minus BA cos delta 1, where in this case, the third formula used when the coil is turning in or rotate in the magnetic field. The coil is rotating. Mostly we use it for motor and generator. Okay, we use in the generator. Ladies and gentlemen, let's observe the next slide. The idea of the Lenz's law. If there is a non-bar magnet and a bar magnet, both of them placed in the same coil or same type of solenoid. So what happened when the bar magnet or non-magnetic bar oscillate in the solenoid? So we notice that if the magnet is oscillate inside the or near to the solenoid, a current is produced, but non-magnet will not produce any current. Helical spring and the bar magnet. Helical spring cause the bar magnet always oscillate. So what happened when we notice that when the magnet is go in, you notice or not certain, there will be a black color arrow in opposite direction. Okay, there will be an arrow, some of the arrow in opposite direction. Now not going in. So the explanation of the Lenz's law is, as the bar magnet is moved into the loops, the magnetic flux experienced by the coil increase with time. This flux is indicated by the red line. The induced current must flow in the direction so as to oppose the increase in the magnetic flux experienced by the coil. To countertract this increase in flux downwards, the induced current produces a magnetic flux upward as shown in black color. Hence, the top surface of the coil must be the north pole and the bottom face a south pole. The north pole created by the induced current opposes the north pole of the bar magnet. This opposing effect creates a resistance to the motion of the bar magnet inside the coil. We observe again when it's moved in, right? What is the magnetic effect? The magnetic effect when the magnet moves into the solenoid, that means they attract each other, right? Attract each other should be, we notice that this will be the north pole, right? When the north pole attract should be this side will be the south pole. North and south will be attract, right? But according to the Lenz's law, the magnetic pole for this one always oppose the effect to produce it. Always oppose the magnetic effect. Just now the magnetic effect is attractive. That means that now they said that must be oppose each other. So north pole and south pole will attract, but according to Lenz's law, it should be repel each other. So that means that this side become north pole. The effect will be repel, you see. Initially will be north and south, but according to the Lenz's law, it become north pole and north pole so that it repel. The motion is going attract each other towards each other, but Lenz's law said that no, must be repel each other. So repel, it become north pole. Once north pole we just can determine the direction of the induced current. So that's why the induced currents always opposite direction to the to the normal current. So induced current always in negative direction, always in opposite direction because of Lenz's law. And because of the magnetic pole produced here should be always opposite the effect of opposite the magnetic effect to produce it. Okay, now let's look at the next slide. What happens when a bar magnet is pulled out? Same thing when a bar magnet is pulled out. Bar magnets pull out, that means the bar magnets move away from the magnet. Move away from the magnet, Lenz said that must opposite. Opposite means well, it must be attract each other. Not pole and what pole is attract. So this will become south pole. Okay. So that means that you notice or not, it becomes south pole. Okay. So this magnet move away. Lenz shows that must be opposite, must attract each other. So north and south will attract each other. Explanation, the same thing. As the bar magnet is moved upwards, the magnetic flux through the coin decreases with time. This flux is indicated by the red line. The induced current must flow in the direction shown so as to oppose the decrease in the magnetic flux experienced by the coin. Oppose, yeah? Opposite. So that means that it will become, okay, south pole. To counteract this decrease in flux upward, the induced current produces a magnetic flux downwards as shown in black. So when we pull out the reduce of the magnetic flux, so cause the restoring in black color. Hence, the top surface of the coin must be south pole and the bottom must be north pole. The south pole created by the induced current opposes the motion of the bar magnet. This opposing effect creates a resistance to the motion of the bar magnet. Okay, so this will be the explanation why the induced currents always in opposite direction, which is explained by Lenz's law. Now, observe that. Go in and out. In and out cause the direction of the induced currents always change. So explanation. Ladies and gentlemen, Lenz's law said that the polarity of the induced EMF is such that it tends to produce a current that will create a magnetic flux to oppose the change in the magnetic flux through the coin. Alternatively, an induced EMF gives rise to a current whose magnetic field opposes the original change in flux. This law is valid even if no current flow as in an incomplete circuit. This will be the case of a metal rod moving in a magnetic field. No change of the magnetic flux, no induced current. From the Faraday's law on electromagnetic induction, so EMF is equal to negative N, change of the magnetic flux over the time, rate of change of the magnetic flux. The minus sign is placed there because of Lenz's law. Lenz's law obeys the conservation of energy. Okay, so that means loss of the red color wave is equal to the installing of the black color, red and black color. Okay, red change to black color. Okay, the effect, and you see the black increase will change to the black color. So reduce. So now the red color increase, so black color reduce. Red color reduce, black color increase. So that means that the conservation of the Faraday's law. Ladies and gentlemen, before that we also learn one that is the, what is that? Whose law is it? Faraday's law. Another one is Lenz's law. So Lenz's law and Faraday's law, what are the difference? Lenz's law mostly state the direction. Lenz's law state the direction of the induced current or induced EMF. Faraday's law state that the rate of change of the magnetic flux change with the speed. Okay, so that means either we use one magnet or two magnet, change of the magnetic field strength. Faraday's law. We move in, out with higher speed. Faraday's law. We increase the number of turns or reduce the size of the coin. Refer to the Faraday's law. Lenz's law just explain the direction of the induced EMF or the induced current only. As a summary, Lenz's law states that the polarity of the induced EMF is such that it tends to produce a current that will create a magnetic flux to oppose the change in magnetic flux through the coin. Alternatively, Lenz's law states that an induced EMF will give rise to the current whose magnetic field opposes the original change in flux. Okay, and the minus sign in Faraday's law, EMF is equal to negative N. Change of the magnetic flux over the change of time is due to the Lenz's law. Finally, the Lenz's law is consistent with the law of the conservation of energy. Ladies and gentlemen, here comes the end of our lesson today. As usual, later I will post the question, the exercise for today's lesson. So what I want you all to do, solve the question first, then you check the answer. So same thing, together, I will post the answer on our Telegram group as usual. Here are the questions for today. We have question 1. Sorry. Question 2. Let me zoom in a bit. Question 2. Question 3. Question 4. Question 5. Question 6. That's all. Okay, so please solve the 6th question and check the answer. So thank you very much for today's lesson, and we continue again on next lesson. Thank you and see you. OK， so 那么各位同学有什么问题要问吗？